Hello, my name is Casper and I'm from the University of Manchester, and I'm going to talk to you about power hammering through glitch amplification. Recently, there has been a rise of FPGAs used in cloud computing services. In order to improve the cost of these services, it would be beneficial to get the maximum utilization out of the provided FPGAs. Resource elasticity can definitely help you with that. As you can see from the examples on the slide, with resource pooling, wildly different applications can share a common FPGA. Therefore, many companies are working towards this increased efficiency. There is a catch though. Having clients manipulating the same hardware remotely opens up new attack vectors. Our research is working towards solving this security concern where the vendor tools are currently lacking. Well-known malicious design elements are ring oscillators. They can be used in legitimate designs, but they open up way too many opportunities to be used maliciously, such that they aren't allowed on Amazon F1 instances. They can be used to create denial of service attacks or time-to-digital converters to monitor system parameters. As a side note, some of the hopefully not too distracting designs below show ring oscillators which currently aren't detected by vendor tools, whereas they are detected by the tool used for this paper. But there is an alternative way to draw an excessive amount of dynamic power to cause disruptions. That way is glitch amplification. In this talk, I'm going to briefly go over how to estimate power to highlight the seriousness of glitches. Then I'm going to show you how to construct malicious glitch amplifying circuits. And lastly, we're going to look at our proposed mitigation methods. On this slide, you can see a well-known formula to calculate dynamic power draw and all of the definitions for the variables. Most of these factors are outside of the cloud user's control, except for one. The one parameter any user can manipulate is the transition density at a node. We know that we can have a transition density at a node be larger than 1 through glitching. Thus the circuit is faster than the clock speed. Various works estimate that from 20% up to 70% of dynamic power dissipation comes from glitches. Therefore, a design with deliberately many glitches pushes the upper bound of the previous estimation even further, and then we have a serious problem. In this paper, we are describing a way to generate glitches which uses a very small amount of resources, and which can be easily inserted into normal-looking designs to hide the malicious intent. The design consists of two elements. On the left, we can see a glitch generator which has a toggling flip-flop sending a single signal to a lookup table. That single signal arrives at the different inputs of the lookup table at different times, which causes it to glitch, as we will see soon. On the right-hand side, you can see a simple power-burning network, which can be constructed out of any leftover routing wires. This will be the main part of the design, drawing a lot of power. On the bottom of the slide, we can see a waveform with most of the signals represented. By progressing on the waveform, we can see that with the rising edge of the clock signal, the first signal has reached the XOR function implementation, and the power-burning network has switched its value. And now we can start seeing how the glitch amplification is working. With different delays, the staggered input arrival is starting to switch the power-burning network values faster than the clock. With a little jump in time, we can see that even after the falling edge of the clock signal, the system is still glitching. And after a full clock cycle, we can see that the power-burning network managed to switch its value 6 times, using a very small amount of primitive resources. So we experimented with the vendor tools to see what they pick up if we use a different amount of inputs for the lookup tables. The whole malicious design, which was 47 of these glitch generators, just uses 0.03% of flip-flops and a 0.8% of lookup tables on the Ultra 96 board. The power-burning network took a quarter of the routing resources and less than half of the flip-flops to anchor down the routing with transparent latches. From the table, we can see that much isn't needed to crash the chip. The board needed a full reboot to become usable again. It is crashing because the power consumption of the board is already exceeding the power envelope of the board, which is about 12 watts. Additionally, an attacker could amplify the glitch even more than we did to have a smaller power-burning network. In conclusion, this attack is relatively simple to implement and is a valid concern. In order to deal with this serious security issue, we decided to improve FPGADefender, which is an open source tool developed by us to scan bit streams. The brief overview of the tool can be seen on the slide, where the netlist is generated using another open source tool called Bitman. That netlist is scanned against different virus signatures with different configurations for different ports and setups. The scan results can then help decide if the bitstream is safe to load into the FPGA. The scans are done at bitstream level to ensure that nothing malicious is inserted into the design before, during, or after the bitstream generation by any party. Now we're going to see how the glitch amplification signature scan works by stepping through the process used in the scan. On the slide we can see an example netlist which has a simple 6-input lookup table with the configuration value above it. First, we have to minimize the lookup table value using a tool called Espresso. With the minimized value, we can see that input 1 and input 2 were redundant for this particular function, so we cut those connections. Next, we start finding scores for every wire between any two flip-flops. A glitch score essentially represents how much a wire can switch per input signal change. Once we reach a lookup table, we find out how likely it is that the output changes its value with that specific implemented function. In this case, it is 62.5%. If the 05 wire was in the netlist as well, it would be processed separately with its own minimized lookup table configuration value. Now we can see that the glitch score on the 06 wire would be 0.625, with one wire going through the lookup table with the initial glitch score of 1. Next, we start looking at the input wire 2, and that wire glitch propagation increments the glitch score of the 06 wire as seen on the slides. So we do the same with all of the wires in the netlist between two flip-flops. Keep in mind that the input of a lookup table could have an already amplified glitch score, which then adds a different value to the accumulated score for the 06 wire. And then we add every value together in the netlist. For the unscored wires in the netlist, we just give them a default glitch score of 1 for now. This example will then give us a score of almost 11. We did scan many different benchmark designs and the malicious design with the new signature scan. From the graph, you can clearly see that the malicious design stands out. Our particular SHA-3 design stands out as well, because it uses a lot of wide XOR functions and bit shuffling operations in an unrolled fashion, which can potentially cause a lot of glitches. It is important to keep in mind though that our model isn't quite accurate yet, because we assume that all of the inputs change at every rising clock edge, and that the glitches always propagate through the entire combinatorial path without any cancelling out effects. So to conclude this presentation, we have shown new type of malicious designs which can be used for denial of service type of attacks. We managed to crash just a small Ultra 96 board, but considering that the VU11P and Alveo cards are produced using the same processing technology, the work presented here is still relevant. Previously, the FPGADefender could detect ring oscillators, high fan-out designs, prohibited ports, prohibited paths, or short circuits. With this work, we have completed the tool to provide a more complete solution. In the future, different parameters of these types of glitch amplification attacks should be looked into to improve the detection accuracy. Thank you for listening, and I would like to kindly thank ERFAS, EuroEXA, and the Xilinx University program for supporting this work.